A2 further maths, differentiating inverse trig functions. What I'd like you to do, please, is I'd like you to differentiate the function y equals sine to the minus 1 of x. And my only hint I'm going to give you at the moment is instead of working out dy over dx, like it asks for there, try working out dx over dy. Okay, so pause there, have a go yourself. I'll repeat that hint. Instead of dy over dx, start by working out dx over dy. Right, have a go yourselves. Okay, so if we wanted to differentiate our sine, what we can't do is we don't know what the actual differentiation of it is. So the first thing we want to look at is rearranging, instead of y equals sine to the minus 1 of x, rearranging it to make it x equals sine y. Now once we've rearranged it to make x equals sine y, we do know how to differentiate sine y. We can rearrange it, we can differentiate it easily, because we know that sine differentiates to cos. Okay, now the issue is we've got dx over dy, and we want dy over dx, but we've also got it in terms of y, and we want it in terms of x. So again, pause now, see if you can rearrange it, and see if you can sort this bit out into x's. Okay, so let's see how far you got. We know that we can rearrange dy over dx because it's just 1 over dx over dy. Alright, so it's just 1 over cos y. So that bit's okay. We're still stuck with this y value though. Now what I would say is we can change, we know that sine y is equal to x. We don't know what cos y is, but we do know that sine y is equal to x. But what we could do then is we could do some sort of rearrangement using a trig identity to write cos y in terms of sine y. Now I know that cos y and sine y aren't linked, but I do know that cos squared and sine squared are linked. So if I change cos y and I rewrite cos y as sine squared, cos squared, then I can rearrange and use it like this. But let's just have a look and see. So I know that x equals sine y. Now if x equals sine y, I know that x squared equals sine squared y. And I also know that if I've got sine squared y, that's exactly the same as 1 minus cos squared y. So if I do a bit of rearranging here, I should be able to make cos y the subject. So I can take that outside, take this aside. 1 minus x squared equals cos squared y. So therefore, cos y equals the square root of 1 minus x squared. And yes, you are quite right in thinking it should be plus and minus. Okay, I'll discuss why it's only the positive version in a second. So cos y is the same as the square root of 1 minus x squared. So really, that can get substituted back into here. And so I get my final answer that if x equals sine y, that implies that the square root of 1 minus x squared equals cos y. All right, so I can work that bit out from there. Why is that helpful? Because then I can put that cos y back in here and I end up with 1 over the square root of 1 minus x squared. And I've answered the question as it wanted. Dy over dx in terms of x. Dy over dx in terms of x's. It's quite interesting to see that the differentiation of sine to the minus 1 of x doesn't involve any trig functions at all. Okay, so let's answer that question of why is it positive? Why do I ignore the negative? Well, if we actually have a look at the sine to the minus 1 of function, okay, there's the sine to the minus 1 of x. All right, it's that function just there. And notice that I'm actually looking for the gradient of it. I'm looking for the gradient function. Well, if you look at the gradient function of it, notice that if you were traveling from minus 1 across to 1, you are always going upwards. It's always positive. Okay, so the gradient line is always positive. It's never pointing downwards, which is the reason why you only take the positive square root. You can ignore the negative. So in the case of sine to minus 1, it's always positive. So therefore we can just take the positive square root of it. We don't need to worry about the negative at all. Right, now you've seen that, see if you could do exactly the same for cos to the minus 1. So you can just duplicate the skills that I just showed you. See if you do the same for cos to the minus 1 of x. Okay, so hopefully you did the same steps. So y equals cos x, therefore x equals cos y. We can differentiate that. We're careful because it's a minus this time. So minus sine y. But using the same skills we just showed, we know that sine squared y, if I do the square root of sine squared y, that's the same as the square root of 1 minus cos squared. And so therefore it's going to be 1 minus x squared. Okay, so you could do it that way. Once we've got that, we can then just check the graph. Notice that in this case, the graph is always going down. So the graph is always negative. But that's sorted with this minus 1. If I took the negative square root just here, when I did plus and minus, if I took the negative square root, the two negatives would make it positive, and it's never positive. It's always negative. So we're only ever using the positive square root when we did this bit, not the negative version, because the two negatives would make that positive gradient, and it's not. Okay, so in both those cases, we can ignore the negative version because of the shape of the graph. Right, just have a quick look at when the values of these are valid. Okay, so when these are valid. Well, I know for a fact that the range of sine x, so the range of sine x, not sine to the minus 1, the range of sine x goes between 1 and minus 1. So therefore the domain of this function is definitely going to be between 1 and minus 1. Alright, because the range of the sine function is between 1 and minus 1, so the domain of its inverse is between 1 and minus 1. So I know that for a fact. Okay, so I know that this is only going to be valid between minus 1 and 1. But there's also another proviso. Alright, we know that that is definitely true between minus 1 and 1, because if I try putting any values bigger than minus 1 and 1, this value here is going to be take away something, and it will get you a negative value under that square root. So it's not just the fact that it's the inverse of sine, but it's also true on this part just here, that x squared has to be between minus 1 and 1 for this bit to be correct. But there's a bit of an issue here, isn't there? If this is actually equal to 1, I get 1 minus 1. I can square root that, but I get 0. Now, because that's 0, 1 divided by 0 is undefined. So I agree that it should be between minus 1 and 1, but it can't actually equal 0. So therefore, this can't actually equal 1 or minus 1 either. Okay, so it's a slightly even more limited than before. Last time it was between minus 1 and 1, great, because it's the inverse sine, or because this bit here is square rooted. But I've also got to be careful I'm not divided by 0. So the limit of this, the domain of this function, is between 1 and minus 1, not included. Same argument can be said for the cos. Exact same argument, which is the exact same reason why you got that. So in your notebooks, grab those down. But truth is, you've got them down in your formula books. And it's worth making sure that you're aware of where those formulas come from in your formula books. Your examiner could expect you to formulate them the way we just showed, by rewriting it as x equals cos y or x equals sine y. Okay, make sure you got down what you need. Okay, so sticking with your notebooks, just get this exam question written down. We're going to look at how to use what we've just done with inverse trig functions to differentiate this function just here. Okay, so you might want to have a go yourself, or you might want to just listen to me going over the solution. Okay, so make sure you got it down, pause if you want to. Okay, so hopefully you've looked at this equation and you thought, right, if I'm going to differentiate this, I've noticed that it is a product of two functions. 3x squared, just there, times by sine to the minus 1 of x there. So I've got these two differentiated. Okay, so what I'm going to do is, first of all, just use the product rule then. So using the product rule is the one where you differentiate a function, leave the other function alone, then differentiate this function and leave this function alone. So dy over dx equals 3x squared. So then I'm going to differentiate this. We need to be careful because you're using the chain rule in here. It's not just as easy as thinking, oh, I can just stick 4x into the formula. you do need to be slightly careful. So in this case, when sine to minus 1 equals 4x, if we let u equal 4x, just to demonstrate where this comes from, then I got y equals sine to minus 1 of u. At this stage, you can use your formula books, because y equals sine to minus 1 of u. If I differentiate this, then I can use my formula and get my 1 over the square root of 1 minus u squared in this case. Okay, so I'll differentiate doing both. So I differentiate this function, and I'm going to get 1 over 1 minus u squared straight from my formula books. I differentiate this function and I get 4. I can then put those parts back in. Okay, so I can put the 4x in. The common mistake people make is forgetting that 4 on the top. So be very careful. Don't mess up on your chain rule. Okay, so yes, you substitute in the formula, but don't forget the extra 4 in there. Okay, then what about the other side? Well, the other side is differentiate this and leave that bit alone. So there we go. Left alone differentiated, differentiated left alone. And I've done the differentiation. Fantastic. What I need to do now is I need to think about when is this derivative, what values is this derivative valid for? So when is this appropriate to use? I could put these two together, neaten it up a little bit, 12x squared. And what I'm going to do the valid part is deal with it as two separate bits. So first of all, I'm going to think about the 6x sine to the minus 1 of 4x. Well, I know that sine to the minus 1 of x is obviously valid between 1 and minus 1. Okay, because it's the inverse function, it's limited between those two values. What about sine to the minus 1 of 4x then? That means that the x value is replaced for 4x, and so therefore this is valid between 4x, as between minus 1 and 1. What does that mean? That means that the x value is between a quarter and minus a quarter. Okay, so I've worked out that this equation, or this differential, the derivative here, is definitely only valid between a quarter and minus a quarter, inclusive. Okay, that's a definite. Let's look at this side as well. So on this side, forget the 12x squared, that can be valid for anything. I can put any value in 12x squared. This is the bit that's causing the problem, the 1 minus 4x squared. So what I can do is I can say this is only valid between minus 1 and 1. Okay, what does that mean then? That means that this bit with the 4x is only valid between 4x is between minus 1 and 1. So therefore that 4x is between minus a quarter and positive a quarter. And so it's important to notice that this one doesn't include the quarter, because then it would be divided by 0. Whereas this one, you're allowed a quarter in there, because you can do sine to minus 1 to 0. What does that mean then? It means you pick the smaller out of the two as the overall valid part. Okay, it's no good saying, well, a quarter works here, but it doesn't work here. You've got to say that you've got to pick the smallest one. They can't use a quarter because it doesn't work in this one. So your smaller out of the two dictates your overall valid. So that's where this part would come from here. Okay, so we've done the differentiation and we've worked out what the derivative is valid for. Okay, so like we did at the very start, we looked at sine to the minus 1 and cos to the minus 1. Can you use the same skills to see if you can differentiate y equals tan to the minus 1 of x? Okay, so see if you can work that through. So pause there and we'll go through it in a second. Okay, so let's see. Hopefully you changed it to tan y equals x. So therefore you can differentiate it. We know, we can use our formula books if we want to, that tan y goes to sec squared y. That's what dx over dy is. But we want dy over dx. So the first thing I want to do is just flip it over. There we go. Now what's good about sec squared y is, using the trig identity, I know that sec squared y is exactly the same as 1 plus tan squared y. They're exactly the same. So I could replace the sec squared for 1 plus tan squared y. Why would I want to do that? Well, I know that tan y is exactly the same as x. So really, this goes to 1 plus x squared. And interestingly, unlike the others, because you're adding an x squared in here, there's no minus signs floating around. This is always going to be bigger than 0. and then you can also substitute any values you like. So in this case, just here, this is valid for any x value you like. All right, every single x value, certainly on the real line. Okay, make sure you got down what you need. Okay, so let's move down to hyperbolic functions. And what I'd like you to do, please, is just use the same skills that you did with trigonometric functions to work out the derivatives of the inverse hyperbolic functions. Okay, using exactly the same sort of skills. Okay, so let's see how far you got then. So for sine to the -1, or r sine, we rearranged it. We made x equal sine y. We differentiated it, and of course sine goes to cos. We can substitute that, we can rearrange it to get dy over dx. But then we also know that sine squared and cos squared are linked together. We know that cos squared is exactly the same as 1 plus sine squared. So just check what I've done there. I've squared it and square rooted it. So I've wrote it as square root of cos squared y. And I know that cos squared y is 1 plus sine squared y. So what does that mean then? It means your end answer is 1 over the square root of 1 plus x squared. Can you do the same for the other two? Well, hopefully with the cos one, you rearranged it, you changed it to cos squared y, you differentiated to sine, because cos just goes to sine, you flipped it over, so you got 1 plus 1 over sine y, but then same idea as this one here, but obviously just going to be slightly different way around. Is going to get you, if I square it, I get sine squared and square rooted it straight away, it's the same thing. And therefore get to this. You're quite right to think where's the negatives gone. We'll have to look at the graphs in a minute to show that. So once I've got that part just there, this is going to go to 1 over x squared minus 1. Subtly different between those two, and also different to the previous ones as well. Okay, so they're different, slightly different answers. Finally, tanh. So the r tanh to the r tanh is going to be, change it around to tanh y. Differentiate it, this gets you sech squared, and we know that sech squared and tanh squared are slightly related. We can see that because you can get it from the same one of these. And once we've got that, we can substitute it in and gets you 1 over 1 minus x squared. Now that one's obviously going to have some sort of limit to what's allowed. Same with these, because you don't want to be divided by 0. For example, x can't equal 1. X can't equal 1 in this case either. So we need to be thinking about the limits of these derivatives. Okay, but just look, you've got 6 different ways of writing it there. You've got 6 in the trig, all very different, all slightly different, sorry. Just got changing around of the x squareds and the y's, the x squareds and the 1's, and changing whether it's positive or negative. Okay, so let's have a look at what. So just in your notebooks, let's make sure we got these hyperbolic functions written down. So the first one we looked at was sine to the -1. And we realised it went to 1 over 1 plus x squared. Now what's important about this is this works for any value. You notice that it's not valid, it's valid for any single value, it's not undefined for any x values, because 1 plus x squared can never be equal to 0, and it's always positive because you're adding a positive number to 1. So therefore it's valid for all values. But why did we ignore the minus sign when we rearranged it? Well, that's when you look at the graph. So when we look at the graph, it's always positive. No matter how far down here you are or how far up here you are, you're always traveling upwards as a positive gradient. Okay, however much it levels off, you're never going down. So therefore we can ignore the negative version of the square root, and we just looked at the positive version of the square root. Right, what about Archos? So for Archos, we can see that we got 1 over the square root of x squared minus 1. This one is defined between certain values. In this case, we could look at the x value being between -1 and 1. Okay, so the x value is between -1 and 1. If it's between -1 and 1, it's going to be too small, because when you take away 1, you're going to get a negative value there. So it has to be bigger than -1 and 1 for it to be defined. Okay, but why not the negatives? Well, that comes from the fact that the graph if you look at the graph of cosh function, you notice that it's only from 1 upwards. So when we talk about what it's defined by, which x value is appropriate, because the actual function itself, it only works for 1 upwards. Now, we can't put number 1 into it because number 1 is going to get you 0. That is the reason why it's only greater than 1, not equal to it. And that leads on to tanh. What about the tanh function? So for the tanh function, you get 1 over x squared. And the same reason as the other one, it's not going to be, we didn't have a situation with the square roots, we don't need to worry about plus and minus, but we can clearly see here that we're taking away an x squared. So this could be negative, and it'll be negative if x squared is bigger than 1 or smaller than minus 1. So it's only defined between minus 1 and 1. It can't equal 1 because then you get that as 0. But there we go, you can see that it's always an increasing function, which is why this is always going to be positive. Always going to be positive. These are given to you in your formula books, so you don't need to learn any of them, you just need to make sure you can use them. Right, now that you've learned them all, what you need to do is just have a go at practicing them. So can you have a go at practicing either using the appropriate trig or appropriate hyperbolic function to solve those questions?